I want to go back and for a minute simply review the Big Bang. Because I think there's a question that comes up in everybody's mind when we start talking about the Big Bang, and that is why it didn't produce all of the elements that we see out there in the universe. And let's take this diagram, because this diagram, we've been over this diagram before, but this diagram will help show why we didn't form all of the elements in the Big Bang. Now, a couple of important things to tell you about before I discuss this diagram. The first thing is that a neutron outside of the nucleus of an atom decays, and it has a half-life of 887 seconds. So what does that mean? That means that in about 7 half-lives, a neutron's going to be all gone. If they don't, the neutrons that existed in the Big Bang are going to be all gone. And if that happens, we don't get them into the nuclei, it takes about 7 half-lives to completely use up everything, almost everything. And so if that happens, we don't have any atoms in the universe except hydrogen. So we need to get the nuclei in the atom to start forming bigger elements, the neutrons. So the way to get neutrons in there, well, as it turns out, the photons in the early part of the universe were more energetic than deuterium. So that is that deuterium forms rather easily by adding a neutron, but then a photon breaks down deuterium quite easily. You may remember, of course, deuterium is just made up of a neutron and a proton, as you can see here in this diagram. So in the early universe, you've got these neutrons being added to a proton to form deuterium, but then these nasty photons are breaking up the matter. And that's what's going on early in the earliest part of the universe. But then again, we have a limited time because of the decay. It turns out that after 90 seconds, you get the photons calm down enough to where when deuterium starts to form, the photons can't break it apart. And then that's when we're able to go through these reactions. You form deuterium, deuterium goes to helium-3 and tritium, and then helium-3 and tritium go to helium-4, and basically helium-4 is the stable isotope, or stable atom of helium. You can form some beryllium, you can form some lithium, but in general it goes back to helium-4, although there is a little bit of lithium and a little bit of beryllium that's generated by the Big Bang, but that's it. And the reason that we can't form the other elements in the universe is because the energies by this time, when we start to finally form helium-4, are too low. And that's because we had to wait so long for the deuterium atom to form. Because without deuterium, we can't form helium-3 and tritium, and therefore helium-4. So we had to wait for the energies to reduce, but by the time we get to helium-4, there isn't enough energy to fuse helium-4 up to carbon. Eventually it goes to carbon through fusion. So we're left then with a universe that has hydrogen 75% and helium 25%. So we've got a universe that is very specific, and you know, I hate to keep emphasizing this, but those people that poo-poo the Big Bang, I mean, you got to explain why we would predict 75% hydrogen and 25% helium, and that's basically what we see throughout the universe. It's another compelling argument that there was a Big Bang because we see precisely what we'd anticipate. So the big question of interest to us is, how do we get all those elements bigger than helium? Now let's take a look at the chart here. This is actually the concentrations, log of the elements in the sun. And first thing that should stand out is that hydrogen and helium, because it's a log scale, it's not that separated, but hydrogen and helium are the most abundant elements in the sun. Turns out 71% hydrogen, 25% helium, a little bit less hydrogen than what we would expect from the Big Bang, but that's because we've had some elements converted to other elements. And as you can see, there's some significant abundances of other elements here. Iron is in 0.12% in the sun. We have a significant amount of oxygen and carbon, some silica. Those are all very important elements when you're talking about forming places like the Earth, which we'll go into in more detail when we discuss the solar system. Now I want to focus on a very famous diagram. This is the number of nucleons in the nucleus, essentially protons and neutrons, and the average binding energy of each nucleon. And all that means is that that's the amount of energy it requires to break down the nucleus into protons and neutrons, essentially. And so it gives us an idea of what happens when you fuse two elements, like two atoms of hydrogen. You're going to generate helium-4, which produces energy. And you keep producing energy all the way up the scale as you fuse these elements. So if you fuse helium-4 to carbon, and then carbon to oxygen, you keep producing energy all the way up to this magic element, iron-56. I say it's magic. It's kind of an important element. Actually, you fuse all the way up to nickel-56, and then nickel-56 decays back to iron-56. So you're in this range of nickel and iron at 56. And then after that, it actually requires energy to make the other elements through fusion. So fusion is important in making the elements up to iron-56, but after you get past iron-56 and nickel-56, we got to rely on some other method, and it's primarily called neutron capture. Now, I won't come back to the specific diagram, but I'll come back to the things that I've brought up in this diagram. We know about fusion, so now we have to start concentrating on the neutron capture of the diagram. The best place to start in this evolution of the elements is to talk about our own sun and what happens. I've already talked to you a little bit about it, about this gravity and gravitation collapsing towards the end of its life, and then the fusing of helium into carbon. But there's a little more to it than that. When it starts going through this red giant phase, it starts to take two helium, they're called alpha particles, and fuses them to beryllium, giving off gamma radiation. And then you get beryllium going to picking up an alpha particle, a helium particle, or helium atom, and making carbon, giving off a gamma ray reaction. Very famous reaction. You know, this has been studied with great intensity because nuclear bombs are used to kill people, so we put a lot of money into things that kill people. We can debate the politics of that, but we have an awful lot of information about this particular process. I should tell you that once the white dwarf is formed, we have primarily, when you get a white dwarf formed from a star the size of our sun, you generate carbon-12. So carbon-12 is about all you're going to get. You're going to get a little bit of oxygen, you're going to get a little bit of neon, a few bigger elements, but for the most part, small stars like the sun pretty much stop at carbon. Maybe a few other little things. Now, I should tell you something kind of interesting. A white dwarf, if you take a teaspoon of a white dwarf, that sucker weighs 1 ton. So you get an idea of the immense density of these white dwarfs. And you may remember I told you that the red giant phase happens with stars like the sun and all the way up to 8 solar masses. So we can expect this kind of fusion to take place if a star is 8 solar masses or less than the sun. We go through the red giant or white dwarf phase. We've already talked about supernovae type 1a or type 1s. Those are if you remember, those are the binary star combination where you go from one of the stars forms a white dwarf, then the other one goes through the red giant phase, and well, the first one went through the red giant phase too, and then formed a white dwarf. Well, when the second one goes through the red giant phase, that white dwarf sucks all the material into it, and that then creates an instability. Everything wants to pressurize and blow up, and you create a supernova type 1a. But there's another way you can form a supernovae, and that's through a process basically of a big star collapsing in on itself, and if these stars are bigger than 8 solar masses on up to about 16 solar masses, you create an explosive environment. And I want to talk about that in some detail, because it's a process that gives us all of the elements, it's believed, or all the rest of the elements. So think about this, if you will. We've got one of these large stars collapsing, and it's going to be quite a bit like the sun. You're going to collapse it, and you're going to start to form in the core. After you've used up the hydrogen, you're going to start taking helium and converting it to carbon, and then carbon is going to be further collapsed, and it's going to fuse and form oxygen, and it's going to keep going, neon, and all the way up to nickel 56 and iron 56. And when you get to that point, you can't go further because it requires energy. You might make a few elements, but those elements, remember, that you're fusing are starting to take away energy from the system, so the star starts to cool down. So it's believed that you can't make the bigger elements necessarily through this process. You need another process, which I'll talk about in a minute. And so another thing that happens when these big stars start to collapse is that you get this outrush of neutrinos and very small particles. Billions of them travel through the Earth every day and hit nothing. And this rushing out of neutrinos is believed to cause an instability in the star, and it explodes. And these things are phenomenally bright. And just to show you how bright, this is a star in another galaxy, and it exploded in 1987. And the star on the right is what it looked like before it blew up. By the way, it's called SN 1987A. And then on the left, you can see what it looked like after the supernova. Again, immense amount of energies being generated during this star production. And by the way, we detected neutrinos on Earth. Well, the question, of course, comes, how do we make those elements? Well, let's go through a little review of supernovae for a minute, and then we'll get to the processes involved. This fellow, Fritz Zwicky here on the right, he studied supernovae in the 1930s, and he discovered that there were basically these two types of supernovae that we've talked about. Type 1, where the spectra has no hydrogen, and then type 2 supernovae, where the spectra does have hydrogen. And I think if you think back on how type 1 supernovae form, that is from this binary star combination, where it's a white, one of the stars is already a white dwarf, you can expect that explosion isn't going to have much hydrogen, if any at all, in it, because it's burned up, the white dwarf has burned up all of its hydrogen. So those kinds of explosions we would expect to have very little hydrogen in them, just as Fritz Zwicky discovered. The type 2 supernovae have hydrogen, not only hydrogen, but all the other elements. The Crab Nebula here is an example of a type 1a supernovae, and we have evidence that the Chinese documented the explosion of this type 1 supernova. We can measure the speed of those gases. Now you're looking at a cloud that's expanded from a center, and all of that cloud is moving away from the center, so we can calculate the speeds that each one of those particles is moving in that cloud, and then we can extrapolate back, and it turns out that it fits nicely with an explosion occurring in 1054 AD. Just as an aside, I thought this was kind of interesting. Out in Chaco Canyon, in the American Southwest, there's looks like what is a star on a petroglyph. So maybe that was a documentation of the 1054 supernova. We'll have no way of knowing. Well, this is what the supernovae 1987A looks like today. You can see the ring. So this has been expanding from the explosion, and we're seeing all kinds of different elements in that explosion. We can use the mass in that ring to determine that the star was about 15 times the mass of the sun when it exploded. We have in the center sometimes the protons and electrons will go together because of the immense density. They'll go together to form neutrons, and so everything in the star is basically turned into neutrons, and we form in the center of a lot of these supernovae what we call neutron stars. So we'll talk more about neutron stars a little bit later on, because sometimes, well, they tend to spin. They're very small, and sometimes if the starting star is big enough, you can form black holes, and we'll talk about how neutron stars might go to form black holes. So this neutron star is about 10 kilometers across. It's not very big, considering the fact that you started out with a star that's 15 times the solar mass of the sun. And of course, it's exploded, so a lot of the material has been sloughed off into space. But the important point is that it is dense, and these things can form black holes, neutron stars. If the star starts out big enough, of course, you can go to a black hole. And supernovae stars form if the star is greater than 8 solar masses and 16, between 8 and 16 solar masses. After you start getting bigger than 16 solar masses, you start to make neutron stars that turn into black holes, it's thought. These are the people that discovered how we form elements larger than iron. Through, we form iron through fusion processes, but you can also now form the other elements, if you remember, through neutron capture, but there are various processes involved here, and these are the 4 people that documented that process. Burbage, Fowler, and Hoyle. They're often referred to as B2FH. I guess it's a little play on a chemical formula there. But anyway, they won the Nobel, or I should say what they discovered won the Nobel Prize in 1983 for their discovery. When I was in grad school, I had to read their paper. The paper's about that thick. But honestly, it's very, very interesting read how the elements in our universe form through this supernovae process. Now, I'm showing you this diagram, but I want to emphasize something, and that is that this diagram is just part of the periodic table. But we can extrapolate the processes I'm going to show you here to the rest of the periodic table. So don't think that this is the only place where these processes are taking place. We're looking at the neutron capture here process and a proton capture, and these processes are going to occur to form all of the elements in the periodic table that are formed in supernova, and we'll see which ones are formed after I explain this process. The first kind of process I want to talk about is the S process. S is short for slow process. This is a process that occurs usually without a supernovae, so we're forming it in stars that aren't producing many neutrons to be captured, so that's why it's called the slow process, which would be primarily red giant phases. First, a little bit about the diagram. On the x-axis, you're going to see the addition of neutrons, whereas on the z-axis, when we increase an element, you're going to see the addition of protons. You may remember from high school chemistry that when you add a proton, you change the element. For example, if you add a proton to silver, you're going to create cadmium, and cadmium, add a proton to that, you're going to get indium, and on up the scale. But if you add neutrons, then you're just changing the mass of the atom, and we create isotopes that way. So cadmium-110 is an isotope of cadmium, and if you added a neutron to it, you'll get another isotope of cadmium, cadmium-111. Now let's talk about the S process through neutron capture. Basically, that is what the S process is. It's documented by the red dots and blue arrows here. And we'll start with silver. Silver 109 captures a neutron and goes to silver 110. And then it decays, it's unstable, and it decays back to cadmium 110. And once you have cadmium 110, then it can capture a neutron and go to cadmium 111, and you go down the line, 112, 113, 114. Turns out that when it forms cadmium 115, cadmium 115 is unstable, beta decay again, it goes back to indium 115, stable isotope, but that can capture neutrons, and you get the idea. You go on and on and on. Now, in the rapid process, this is where you're producing a lot of neutrons, which happen in supernovae, in particular the type 2 supernovae that we've been talking about. And in that case, the reason it's called rapid, if you look at cadmium-114 here, you are creating cadmium-115, but it decays away rather rapidly to indium-115. So it means that we've got to add a neutron to make cadmium-116 before cadmium-115 decays away to silver-115, because cadmium is an unstable isotope. Cadmium-115 is an unstable isotope of cadmium. And that's how we make cadmium-116. The black arrows that you see on here are this R process taking place. You see up there at the tin, you're creating tin-122 the same way. You catch the tin-121, add a neutron to it before it decays away to antimony-121. And finally, we need a way to create things like tin-112. And in this case, we have to add some protons. And you do have protons produced in the supernovae and some red giants. So you can convert cadmium-110 on up to tin-112 by adding 2 protons. And so now you have all the processes, with the exception, of course, of fusion, which we've already talked about, that generate the elements that are larger than iron and nickel that we talked about, the iron and nickel 56, that is the kind of the end result of the fusion process. And so finally now we're at a stage where we can discuss the periodic table and talk about how all of the elements have formed. First of all, you see hydrogen and helium there. Hydrogen and helium were formed in the Big Bang, so we know how they formed. But then lithium, beryllium, and boron, they're formed by cosmic rays in our atmosphere. Don't have to mess around too much with that. The elements in the purple are made by humans. The small stars are things like the sun, and when they go through their red giant phase, the sun will stop at carbon. The other elements in green, those are made by the big red giants when they form. And then finally you have all the elements that are created by the supernovae, type 2 supernovae for the most part. And so this is in general the way we get the elements. The only thing left to tell you about is something I find quite remarkable. I'm going to point to technetium here. Technetium doesn't have any stable isotopes. So when technetium is created, it decays away. Technetium has a half-life of 211,000 years. So that means that after about 7 half-lives, technetium is going to be gone. It's going to decay away. That's about 1.5 billion or million years. The Earth is 4 billion years or 4.5 billion years old, so we lost technetium a long time ago. You will not find technetium on Earth. But oh, guess what? If we look in red giants, where we believe technetium is supposed to be formed in the super red giants, we find technetium. Now you might argue that the elements that we see in the spectra of these large stars were due to something else. But it's hard to imagine that technetium isn't being created by that process that's going on in those large stars. So we have some indications that these elements are actually doing what we think they're doing and being created. I just want to mention that there's some talk, we have these cosmic gamma ray bursts throughout the universe, and there's been much speculation as to what's causing these. In fact, they're the most energetic things in our universe, and they're thought to occur when 2 binary neutron stars merge, and if they don't form a black hole, these might be other sources of elements. But the main thing is to leave you with is that these elements, because of supernova explosions taking place, or red giants expanding, that these elements get dispersed all over the universe into these clouds. And so we have a case of where the elements that are required must have been going into clouds that collapse to form our sun. We see very few stars out there. Well, we don't see any stars that don't have some elements other than helium in them. So we know that most of the death of stars have come and gone, and interestingly enough, were made of the ash left over from the stars.